In the last class, we have seen what is narrowband fading. What are the conditions that arise with narrowband fading channels? We have derived its autocorrelation and power spectral density functions. Okay. Today, in this session, we will be studying what is wideband fading. How we are going to model a wireless channel when under wideband fading conditions. In case of wideband fading model, a short transmitted pulse of duration t will result in a received signal that is of duration t plus tm, where tm is a multipath delay spread. Thus, the duration of the received signal may be significantly increased. If the multipath delay spread Tm is much less than T, then the multipath components are received roughly on the top of one another. Narrowband fading. On the other hand, if the multipath delay spread Tm is much bigger than T, the earlier condition where Tm, the delay spread as a whole, is much less than the duration of the pulse, we call it as narrowband fading. That is, we have a delay spread. There is a time pulse and we have a delay spread. We are adding a value of Tm to that. If Tm is much smaller than T, we call it as narrowband fading. When Tm becomes bigger, we call it as wideband fading. On the other hand, if the multipath delay spread Tm is larger than T, then each of the different multipath components can be resolved. That is, when the delay spread is higher or when the signal, while multipath propagating, reaches the destination at a different point of time, at a larger points of time, then it is all resolvable. All multipath components would be resolvable in that case. Am I right? Yes or no? So that there is a wide band. The next slide I will be explaining to you with the necessary waveforms. On the other hand, if the multipath delay spread Tm is less than T, is greater than T, then each of the different multipath components can be resolved. However, these multipath components interfere with each other and subsequently with the transmitted pulse. This effect is called as intersymbol interference. So what happens here? Intersymbol interference. You have a pulse of duration T and this pulse is being transmitted from the transmitter to the receiver. Okay. When this pulse T is received at the receiver, due to the multipath components, we have a delay spread and that delay spread is represented by Tm. So what happens? There is an increase in pulse. This would naturally cause an intersymbol interference because it interferes with the previous symbol or the next symbol. There is a pulse transmitted. The duration of the pulse is T. This pulse is received here as T plus Tm. Tm is the delay spread that is being caused by multipath propagation and its components. So, in the final received pulse, you will have a T plus Tm component which would result in intersymbol interference. Okay? Delay spread Tm is much less than T. Then mitigating ISI is not necessary. Am I right? When Tm is smaller, much less than T, then there is no need of any efforts to reduce intersymbol interference, because the chances of this pulse getting interfered with the next pulse, or the chances of the previous pulse getting interfered with the current pulse, will not be necessary. But this can place a significant constraints on data rate. Multi-carrier modulation and spread spectrum actually change the characteristics of the transmitted signal to mostly avoid intersymbol interference. But they still experience multipath distortion due to frequency selective fading. Frequency selective fading. What is frequency selective fading? We will be studying in detail in the coming slides. As the transmitted signal bandwidth B increases, the approximation that U t minus tau n of t is approximately equal to U of t stands invalid. What is U of t? What is U of t? The low pass equivalent of the transmitted signal. U of t is the low pass equivalent of the transmitted signal. U of t minus tau n of t will not be approximately equal to U of t, because we have a higher bandwidth. Thus, the received signal is the sum of all copies of the original signal, where each copy is delayed by time tau n and shifted by a phase of phi n of t. The signal copies will combine destructively when their phase terms differ significantly, and will distort the direct path signal when U of t minus tau n differs from U of t. U of t minus tau n of t is approximately equal to un of t only under narrowband conditions. This does not apply when the signal bandwidth is relatively large to the inverse of the multipath delay spread. If the number of multipath components is large and the phase of each component is uniformly distributed, then the received signal will be a zero mean complex Gaussian process with a Rayleigh distributed envelope. Wideband fading differs from narrowband fading in terms of resolution of different multipath components. For narrowband signals, the multipath components have a time resolution that is less than the inverse of the signal bandwidth. So the multipath components combine at the receiver to yield the original transmitted signal with amplitude and phase characterized by random process. These random processes are in turn characterized by their autocorrelation or power spectral density and instantaneous distributions. With wideband signals, the received signal experiences distortion due to delay spread of multipath components. So the received signal can no longer be characterized by just the amplitude and phase. Power spectral density is the Fourier transform of autocorrelation function. You are converting this into time domain. I hope you remember that R of t is equal to minus infinity to infinity A of t into A conjugate of t minus tau. You remember this, all of you? The effect of multipath on wideband signals must therefore take into account both the multipath delay spread and time variations associated with the channel. So there are two components, multipath delay spread and time variations. We have to consider both these things while we analyze the effect of wideband signals. While analyzing wideband signals, we have to consider both the multipath delay spread and the related time variations. So coming to the mathematical modeling of wideband fading channels, the deterministic scattering function of the equivalent low pass impulse response C of tau, t is its Fourier transform. It is denoted by SE of t, rho, that is equal to the Fourier transform of C of tau, t, which is equal to minus infinity to infinity C of tau, t e raised to I 2 pi rho t dt. We are taking the Fourier transform of the impulse response, and this function is known as deterministic scattering function. The time varying channel impulse response is random. It is not deterministic because of the random amplitudes, phases and delay of the random number of multipath components. The statistical characterization of C of tau, t, the impulse response, is thus determined by its autocorrelation function defined as AC tau 1, tau 2 t, t plus delta t. This is the autocorrelation function of the impulse response. You might face questions like deterministic scattering function. Define what is deterministic scattering function in wideband channel modeling of wireless communication systems. Assuming that our channel model is WSS. What is WSS? What is WSS? We are assuming that what are the two conditions for a random process to be WSS? Bit louder. I am not able to hear you. In this case, the autocorrelation becomes independent of the impulse response. In real-time environments, the channel response associated with a given multipath component of delay tau1 is uncorrelated with the response associated with a multipath component at a different way, tau2 not equal to tau1, since the two components are caused by different scatterers. We say that such a channel has uncorrelated scattering, or it is called as US. We denote these channels as WSS-US. US stands for uncorrelated scattering. So we are going to design a model for WSS-US. We are going to design channel models under the condition that the channels are WSS and uncorrelated scattering. WSS-US. In that case, expected value of C conjugate of tau1, T, C, tau2, T plus delta T. This delta T is the multipath component, is equal to the autocorrelation function of T1, delta T, and is defined as so. It is not actually. Now taking the Fourier transform and working out in the frequency domain the autocorrelation function of F1, F2, taking a time delay of delta T, will be equal to the expectation of integral minus infinity to infinity C conjugate tau1 T e raised to j 2 pi F1 tau1 d tau1, the F1 component. Similarly, tau2 C minus infinity to infinity impulse response tau2 T e raised to j 2 pi F1 tau2 d2 d tau2. On simplifying this equation, we will get the autocorrelation function F1 F2 of delta T to be equal to minus infinity to infinity the autocorrelation AC T delta T e raised to minus j 2 pi F2 F1 tau d tau. So So we came to understand that the autocorrelation function F1 F2 delta t will be equal to minus infinity to infinity AC t comma delta t e raised to minus j 2 pi f delta f tau d tau. So we have now derived that the autocorrelation function of a wideband fading model under two frequency conditions F1 and F2, the change in frequencies which is delta f and the time delay is delta t, AC autocorrelation function delta f comma delta t is equal to minus infinity to infinity ACT e raised to minus j 2 pi delta f tau d tau. Derive the autocorrelation function for a wideband fading channel model, or derive the equation for autocorrelation of a WSS-US channel. What is WSS-US? What is WSS-US? WSS uncorrelated scattering. Define power delay profile. Average and RMS delay spread. Both are based on power delay profile. Delay spread is defined as the difference in propagation time between the longest and shortest path, counting only the paths with significant energy. The average delay spread is given as mu of Tm is equal to 0 to infinity tau Az tau d tau by 0 to infinity AC tau d tau. RMS delay spread sigma Tm is equal to root of 0 to infinity tau minus mu tau m Tm the whole square AC tau d tau 0 to infinity AC tau d tau. A majority of time RMS delay spreads are relatively small, but occasionally there are worst cases, multipath characteristics that lead to much larger RMS delay spreads. Measurements in outdoor environments show that RMS delay spread can vary over an order of magnitude within the same environment. Delay spreads can have a major impact on system performance. So we have seen wideband fading models and power delay spread average and RMS delay spread. We are going to study what is coherence bandwidth in the coming section.